Hi everyone, I am Neel Patel and today I am going to talk about our work titled Model Explanations with Differential Privacy. This work is done in the collaboration with Reza, Shokri and Yair. Nowadays, complex ML algorithms are increasingly adopted in high-stake domains such as healthcare, credit decisions and so on. Therefore, there has been several calls for algorithmic transparency and model explanations. However, this additional information in form of model explanation can result in significant data leakage. And surprisingly, there has been a very little work addressing these issues formally. Therefore, in this work, we propose private explanation algorithms that protects the sensitive information about all the data points involved throughout this process. In this work, as a first step, we consider black box approximation based model explanation algorithms. Black box explanation algorithms do not assume or require any access to the model parameters or hypothesis class. Rather, it only assumes access to the model through black box, which basically allows them to query model's prediction on any data points. Such class of explanation algorithms include some of the popular explanations such as LIME, SHARP, MIM, QII, and the list goes on. In order to demonstrate the working of such explanation algorithm, consider this toy example. Here we are given this black box model and an explanation query X, whose decision we wish to explain. Such black box explanation algorithm gathers some of the data points or samples some of the data points around this query and learns their prediction using this black box access. Using this data points, they try to explain the decision of X as they do not have access to the parameters or hypothesis class. And they explain it by generating some understandable decision boundary around this data point X. These data points that were used in order to generate this explanation at X are also referred as explanation dataset. And often these explanation datasets are sampled from the training distribution for better explanation fidelity. Therefore, it consists of real individuals. Recent work shows that if an explanation algorithm uses out of training data distribution points as an explanation data, that can make them vulnerable against manipulation attacks and also can lead to less meaningless explanations. So before we go into the algorithms and other formal methods, first I would like to discuss the privacy concerns of such class of algorithms. Let F be the complex model trained on training dataset D, and there is an explanation algorithm which receives an explanation queries x1, x2 and so on. This black box explanation algorithms first samples explanation dataset, and this dataset is sampled from the training distribution which consists of real individuals. Now this explanation dataset is labeled by this model F using black box access that this explanation algorithm has. Now, given this information, black box explanation algorithm generates explanations for each individual queries. Notice that this explanations contains information about the training and explanation datasets, and therefore an adversary can run multiple such explanation queries and perform reconstruction/inference attacks to construct sensitive information about the training or explanation dataset, which has been shown in the past work. So therefore, in order to mitigate such information leakage, in this work we propose differential private model explanations. So if an adversary observes explanations by differentially private explanation algorithm, then differential privacy ensures that the explanations computed on neighboring datasets, which means the dataset that differs at most one point, are statistically indistinguishable. That implies that an adversary won't be able to figure out whether a particular data point X is part of the training dataset or an explanation dataset, and which theoretically provides guarantees that such attacks cannot be succeeded. In this work, more specifically, we focus on black box approximation based explanations. This class of explanation contains some of the popular existing explanations like line, MIM, QII, and so on. Such explanations, given any explanation query and the explanation data set, it approximates the decision boundary around the explanation query by some simple and understandable classifier, for example, a linear classifier. Our explanation algorithm basically generalizes this and solves this following optimization problem, which essentially does the same. It just finds a linear classifier that approximates a decision boundary around X using explanation data set, where the first term is a weight function that decides the importance of each explanation data point, and the second function linearly approximates the decision boundary. Now for the rest of the talk, I will focus on how to design a private explanation algorithm for this specific class of black box algorithms. So first, in order to protect the training data set, it is crucial to protect the model predictions. Why? Because if an adversary can observe the model predictions, and if they are not protected and leaks the information about the training set, then the adversary can run classic membership inference attack on the training data set by querying just model predictions, and they wouldn't even need explanation queries. However, if the model is trained with differential privacy, then the explanation automatically becomes differential private with respect to the training data set due to the different post-processing property of differential privacy. And that will ensure that our explanation will be differential private and won't leak any further information. On the other hand, in order to protect the private information about the explanation data set, we have to add some differential private randomization to the explanation in order to protect such information. For example, here, given this explanation queries and the explanation data set, if we consider this non-private explanation, that might contain some sensitive information about this explanation data points. However, if we can add some crafted noise to this non-private explanation, then this which can help to hide the information about this explanation data set through this explanation. So instead of releasing this non-private explanation, we would release this private explanation which contains some noise. However, we obtain this privacy by just solving an objective function using some differential private optimizer. However, there are two challenges that we need to still solve. That first is the infidelity due to this differential private randomization should be bounded. That means that the non-private explanation and the private explanation should be close to each other. And the second challenge is that as we explain more and more queries, the information leakage about the explanation dataset accumulates over the time. So therefore, we have to somehow save this privacy leakage and reduce the information leakage over the time, over the queries as we answer more and more queries. Right? The main contribution of this work is our adaptive differential private explanation algorithm, which solves both the challenges discussed earlier. Now, given the sequence of the explanation queries, our adaptive differential private explanation algorithms solves this optimization problem for each query that generates private explanations for the corresponding explanation query. The key observation is that while computing the explanation of data point xi, we can utilize past information released in terms of previous queries or explanation of previous queries in order to reduce the privacy spending, as it contains the information about the underlying model, and this information was already released to the adversary with differential privacy. Our adaptive algorithm utilizes this observation in many different ways and provides an algorithm or framework in order to answer multiple queries over the time with very less privacy leakage as we answer more and more queries. We will demonstrate the performance of this algorithm in our experimental results. Now, the theoretical properties of our explanations basically shows that our explanations are differentially private for explanation dataset. That means that it protects sensitive information about the explanation dataset. Then we show that our explanation leaks strictly less information about the training dataset than model predictions, and this information leakage is strictly less. That means an adversary cannot design more powerful inference attack on training dataset by using our model explanation. That basically means that our explanations do not reveal any extra information about the training dataset than whatever is already revealed through the model predictions. We further show that our adaptive algorithm provably reduce a cumulative privacy leakage of explanation dataset over the time. We further show that the distance between private explanation and non-private explanation goes to 0 in polynomial time as the size of explanation dataset increases. This basically shows that the infidelity due to differential private randomness added to achieve privacy is bounded, as well as it goes to 0 as we increase the size of our explanation dataset. In order to demonstrate the performance of our explanation algorithm on real life, we consider the text dataset, which is the union of IMDb and Amazon movie reviews dataset. We train a model on this dataset that basically predicts whether the rating of the movie is greater than or equal to 5 or less than 5 based on input movie reviews, which basically is like, given this movie review text, model predicts whether it's a good movie or bad movie based on this text. We further generate explanations or the feature importance score or the linear decision boundary, which approximates the actual decision boundary using our differential algorithm, LIME and MIM. Where LIME and MIM are existing algorithms, popular algorithms, explanation algorithms, which generates explanation without any privacy. First, we evaluate our explanation as follows and compare them with existing non-private explanations as follows. So we pick the top influence tokens in the decision making by our algorithm, which is differentially private, LIME and MIM. So here are some of the examples. We can observe that our explanation basically agrees with LIME and MIM, which generates explanation without any privacy. Moreover, we run some statistical analysis as well and observe that our algorithm in LIME shares 3.9 out of top 5 most influenced words on an average. Similarly, our algorithm in MIM shares 2.6 top influence words amongst top 5 most influenced words, which basically shows that our explanation is very close to not even our non-private explanation algorithm, but some of the existing non-private explanation algorithms. Now we show that how our adaptive algorithm reduces the accumulative privacy leakage over the number of queries. So here we plot the graph where the y-axis shows that the privacy budget spent, which is an indication of how much information has leakage, and the number of queries answered. Here we show that the non-adaptive algorithm, which does not utilize any past information, quickly exhausts its privacy budget, where our adaptive algorithm slowly starts to utilize some past information and save some privacy leakage. Where this enhanced adaptive algorithm is more greedy version of the adaptive algorithm, which you can look into the paper. Here we observe that the adaptive essentially spends privacy during some initial queries, like some odd 40-50 queries, and then once it has enough information, it just explains all the future queries with very small privacy leakage.